So if this is a 1 and these are whatever, your leading 0 is going to be somewhere else, so like here and whatever. The next one is going to be like this and whatever. So it looks more like a staircase. But it doesn't have to be straight all the time. It could look longer like that. Okay? So look at it in the picture form.
Do you always have to have all zeros at the bottom?
No, on the bottom it doesn't have to be all zeros. Because if you have 1, 0, 0, 0, 1, 0, 0, 0, 1, that's still in the row echelon form. Actually, it's in reduced. And I'll explain why. So this is 1, everything below 0. This is 1, everything below 0. This is a 1, but there's nothing below. So you could think of nothing below 0. So this is row echelon form. This is in reduced row echelon form because everything above it is also 0. So everything above the leading coefficient and below the leading coefficient is 0. The reason we do this is if we have a system equation and we do this equal to 1, 2, 3, then so we could say, okay, z equals to 3, y equals to 2, x equals to 1. Your solution is already there from the notation and from the form. So that's what row echelon is. Okay. So what I did not explain before is Gauss-Jordan elimination. What we want to do is simplify our matrix so we could get the solution easily. So A, over here where it says set up an augmented matrix. This was an only coefficient matrix because I said it was only a coefficient. But if we have equations x plus y equals to 0 and x minus y equals to 1. If we set this up a certain way where this is, okay, the coefficients of this are 1, 1, 1, and minus x. And now if we put these into the matrix as well, 0, 1, this is our, sorry, this should have been a minus 1. This is our augmented matrix. So this part is A. But like our augmented has this part into it. So and that's dash B. So this is B and this is A. Okay, and B is a vector, A is a matrix. But we put them together into something called an augmented matrix. So what we do is we use elementary row operations to simplify the matrix in a certain way where we get our answer. So if we look at this, we have something complicated. In our case, it's not so complicated. We have 1, 1, 1, 1, 0, 1. We want to make it look as a 1, 1, and over here zeros. So how do we do that? Anyone know? Does anyone know the linear operations we spoke about before? It's switching rows and multiplying and adding, right? So if we have 1, 1, 1, minus 1, and I think I had 0, 1. I don't know. Okay. So if we do, let me call this row 2 and row 3. And row 1. Okay, this is row 1 and this is row 2. If we do row 1 minus row 2 minus row 1, we could get a 0 here, right? So it'll be 1, 1, 0, and minus 2, right? And this is 0, and this is still 1. So if I divide this by 2, so it's minus 2, I get minus 1/2, 1, 0, 1, 1, 0. This is an augmented, and then if I add this row to this row, and minus, okay, if I add the minus of this to this, I get something that looks like this 1, 0, minus 1/2, and then 0, 1.5. Right? Minus a half. So this says that my y equals minus a half and my x equals a half. So if we do a half plus minus a half, that's 0. If we do a half minus minus a half, it becomes 1. Okay? Everyone see that or no? Okay. So this is getting difficult this way. So you know what? Let's just do some examples. And so if everyone, does everyone have a sheet of paper? Okay. So let's work on this together. So people could group up and I'll go around. I don't know the solution to this yet because I'm just making it now. But so we have x plus y plus z equals 1. X. So okay. So if everyone wants to write, please write this down. So I have x plus y plus z equals 2. That's one equation. The other equation is x plus 2y plus 2z equals 3. And my third equation is 2x plus 5y plus z equals 3. Okay? We need to solve this. So first thing is put it into an augmented matrix form. Okay? Then we'd use linear row operations to solve it. And I'll go around for anyone who needs help.